Welcome back to class 15 already. Wow. And we are going to do an example of a refrigerator with a compressor and look through the cycle of this, walk through. And this is example 4.8 from our text, Bornacki. You should buy the book. We're going to use refrigerant 134A as our working fluid, and the mass flow rate through each of the components, because it's only a single path going through here, is 0.1 kilograms per second. The power input to this compressor is 5 kilowatts. The following state data are known right here over this. So they did some things. They were nice of us. They looked some things up. They started here at state 1. And that's right here coming into the compressor, where we had a negative 20 degrees Celsius and about atmospheric pressure, 100 kilopascals, and here's what the enthalpy was. And then we increased the pressure 8-fold to 800 kilopascals, and the temperature went up to 50 degrees Celsius. And the corresponding enthalpy, as you would find if you were to look up in the table in the back, was 435.1 kilojoules per kilogram. And then it went into the condenser. And the condenser is used to, in the back of the refrigerator, is a heat exchanger with some coils and rods and stuff. And it sends this warm, it cools down the liquid. So it was this warm vapor, and now it's a warm liquid. All right, so it kind of condenses. Sometimes there's even a little type of, is that true? No, maybe not. Anyway, I want to take that back. No, sometimes there's like a little catch, a little thing, trap, they call it, as a trap, to make sure that only liquid gets by. And anyway, it's to make sure that we're actually condensing. And I haven't actually messed with refrigerators all that much. Not big refrigeration cycles, but not refrigerators themselves. And then we go here with this warm liquid is now 30 degrees Celsius. We're going to say that it is a saturated liquid, so it's not, it's a 0%. And so here is its enthalpy right here. But then it goes across this expansion valve, which will be an isenthalpic process. But in the process, it changes, it drops pressure and it drops temperature. Is that true? Does it drop pressure? Yeah. So it drops temperature because of it being an isenthalpic process. And then it goes into this evaporator, and that's inside the refrigerator, and that's why it makes it cold. And then we do through the whole cycle over and over again. So this will be something that you do a bunch of times. So this is just maybe the first time that you're running across it, but it won't be the last. All right, so the things that they want to know the quality of the evaporator inlet. Well, let's not just jump right to that. Let's kind of like maybe walk through the cycle, which is generally what's done. So I'm going to go to the compressor first. So we're going to go between states 1 and 2. Between states 1 and 2, and if you'll recall our okay, so in the previous one we did on a per mass basis, we do know the mass flow. So we can go ahead and here's the main equation that we're going to use. We're going to have big Q dot minus big W dot plus, and I could put summations, but there's only one of them. M dot H I minus M dot H E, and we can usually just go M dot H I minus H E. So we'll start out with this one right here, coming across here, and did they tell us anything about here? Okay, so reading through these others, it said the rate of heat transfer from the compressor. What they're saying is there's going to be a little bit of heat loss right across there. So I should have maybe jumped and read the cross of the thing. So you're going to say equals Q dot 1 to 2 minus W dot 1 to 2, and then plus M dot H1 minus H2. So rewriting this thing, because this is what we want to find. I bring this over to the other side, which is going to, and then we're going to change all the signs accordingly. So we end up getting I'm trying to think as I do this right here. I think I'm going to get W1 to 2. It's going to be minus. I think it's going to be. I'm thinking out loud. Sorry. I think I'm going to go minus. Yeah, minus M dot H1 minus H2. I think that's correct, right? I'm trying to get the signs correct because I did it differently on my thing. So we're having work being put in, so that should be a minus 5 coming in. And I think across here, I think I screwed up the signs. One second. All right, so let's say I jump that guy back over onto the other side. That's fine. That would be minus. And then this guy would come over to the other side, and that would be fine. We want a negative value here, but I don't want it to be too negative across the whole thing. So I'm a little concerned about this sign right there. So I'm going to go 0.1 H1 is 387.2 minus H2, which is 435.1. All right, so that's going to be, yeah. If I did it correctly, this should be a negative 0.210 kilowatts. And this is lost energy, right? So generally speaking, that would be 0, and this right here would have been carried by, would be primarily because of that 5 right there, right? So you're going to see that I think that this is a value that's going to be greater than 5. I think so. Yeah, but see, this is negative with a negative. I think we're going to be okay. I think we're going to be okay right there. This is going to be heat lost. All right, so go 2 to 3. So we're going to go from across this right here. And so might as well write this out again. Q dot 23 minus W dot 23. And there's no work done. Plus M dot, and that's going to be H2 minus H3. Did I get that right? I think so. And once again, this should be this should end up being a negative, right? Because heat is coming out of it. So if you're going to go and move it over to the other side, right here, you'd say that you'd have a minus M dot of 0.1 times your H2, which would be 435.1 minus your 241.8, right? And this should be a negative value. Okay, so this is larger than that, right? But then we're going to make it negative. Okay, so it's negative. And then it's going to be 19.33 kilowatts, which was surprising to me, but I guess, compared to that we're putting 5 kilowatts into it. So I was a little wondering about that. That's kind of a strangeness to the thing. But I guess we're getting those the kilowatts by way of what we're taking out of the refrigerator. Okay, so now we go from 3 to 4. So that means we're going to go across this valve, right? So this is a special situation here, where I guess we could go ahead and write this out, but we're going to see in a second that it's most everything goes away. Minus work 3 to 4, or power I should say, plus M dot, and I'm going to go H3 minus H4. But that's going to be 0. Let's say that it's going to be insulated. that's going to be 0. And because the m dot right there, we're going to see that what our conclusion is that H3 equals H4, or more importantly, H4 equals H3. So what you end up doing here is that you had H3 equal to 241.8 kilojoules per kilogram. I think this temperature is a really weird one because most of the time you end up like knowing, I guess. Well, let me put it this way: this is usually a device that throttles on purpose, and I guess you can have a set temperature. Yeah, I guess that's true. You can have a set temperature onto this, and it will throttle accordingly until it can get this. So we want to look up in our tables. And find what the quality is going to be at that at this combination, right? So you look up. Actually, we look up in table B.5.1 at T is equal to negative 25 degrees Celsius. And look that up. And let's see. Let's bring him up. And move that computer over so I can see this. And that's what I say, table B5. B.5. I don't know why we have to have B.5. And 0.1. Yeah, so we're here. We look up the negative 25 right there. And we look for, can we have an enthalpy that's in between these two right here? Our enthalpy, you recall, is going to be 241.8. And you see, yep, 241.8 will land between 167 and 382.9. So we could find what the quality is going to be based on that. So we write out H is equal to HF plus X, HFG, and our H that we're looking for is the 241.8. That was, right before the thermostatic expansion valve right here. This expansion valve thing right there. It was that's what the quality was. It should be the same over here, not the quality but the enthalpy. And now that's going to be times the HF. I mean with the HF 167.38 plus X, and you could call that X4 if you wanted to because it is, and times 215.57, and we get what X2 is going to be equal to 34.52%, and that's the quality, right? So this is what we were trying to find in part A right here, right? The quality at the evaporator inlet, because that's the evaporator inlet right here, and that's what we just did. We could find other things with this, of course. We could find the specific volume and that type of thing. But and then lastly, I think they want to know the rate of heat transfer to the evaporator. So right across here. So I didn't circle these before. We did this one to this one. That was for the compressor. We did this one to this one. That was for the condenser. We just did this one to this one. That was across the thermostatic expansion valve. And now we want to go across to 4 to 1 right here to see. The most important part of this is how much heat that you can get out of your tuna casserole. So this goes to 4 to 1. And so you get 0 equals heat from 4 to 1 minus the work from 4 to 1 plus m dot H4 minus H1. Of course, that goes to 0. This is the main thing that we want. We'll jump it over to the other side. Maybe reverse these. I don't know. Maybe stick a minus sign in front of them. I don't really need to rewrite this, but I did anyway. And so we're going to get 1 point. Was it 1? Did I write 1.5 somewhere? No, I guess I did. I guess I got it right everywhere. Just all of a sudden I decided to go. My brain went to a problem I just recently did. Yeah, that's interesting. So we're going to go 4, which was, well, we just did, right? That was the 241. Sure. 241.8 and minus H1, which was all the way at the beginning at 387.2. Right? And so you find Q4 to 1 is going to do 14.54 kilowatts. And it's positive because it's taking heat into the system. All right, so that was the thing that we wanted to try to find. Now, I should have, but I didn't, right, because I did it in the previous example. I showed efficiency. I should do what's called the coefficient of performance, which is what's used for refrigerators and HVAC plants, air conditioners, instead of using efficiency, but I didn't write it down. I don't have it memorized. But anyway, this was another example, and we'll do some more. Let's see, what are we going to do next? Exciting, I don't know. I'll see. It's a surprise to me. Or we're going to do mixing changes. We're going to do section 4.5 and multiple flow devices. So you got that to look forward to. It's nice to have something to look forward to.